Okay, let's get right back to work on question number 2 here on the empirical formula, molecular formula, and percent composition problems assignment. Number 2 is a lot like number 1. So if you did number 1 earlier on and you've already got a pretty good handle on it, I would encourage you to just pause this video completely and just go ahead and jump to the end after you've done the work and see if you get the right answers, just to avoid you having to listen to me talk and just to kind of step out there on your own and see if you can do it. I'm going to go through it just a little bit quicker because the process is more or less the same on this one, so I won't take a lot of time with it. But we'll start out with the first part of it. It says we've got a compound again containing 4 elements. So we've got carbon, hydrogen, oxygen, and nitrogen. And it tells me that I've got a 1.176 gram sample of the compound, and that it's found to contain some carbon, some nitrogen, some hydrogen. So like last time, it left an element out. In this case, it's left out the oxygen mass, so we're going to have to figure that out by subtraction, kind of like we did in the last one. So we're not actually going to use the 1.176 to do any mole conversions. We will use the masses that are given. So we've got 0.694 grams of carbon is one part of it. We've got 0.090 grams of nitrogen. And we've got 0.084 grams of hydrogen. So we know there's some oxygen left because the first sentence says there's oxygen involved. So what I'd probably encourage you to do here first is go ahead and let's figure out how much oxygen we've got. So I've got 1.176 grams total. Take away the carbon, which is 0.694. Take away the nitrogen, which is 0.090. And take away the hydrogen, which is 0.084. That should leave us with 0.308 grams of oxygen. So 0.308. So there's our 4 parts. So again, just by subtracting all the other ones out, we've got our final constituent figured out. And I'm going to go ahead and do conversions like we did in the last one. Carbon gets converted to moles, nitrogen gets converted, hydrogen, oxygen, they all get converted to moles. Because again, we can't relate grams to grams and write an empirical formula. A formula is based on the atom to atom ratio. And the way we count atoms is by counting them up in moles, because atoms are way too small to count. Okay, so 1 mole of carbon. Again, like in the last one, we're going to need to go to our periodic table here and look at the masses for the various elements. And you can look up them just like we did in the last one. But there's carbon. We need nitrogen, oxygen, hydrogen. They're all here. So the atomic masses that are listed there, we're going to go ahead and use. Carbon is 12.01. Again, one that you'll use a lot this year and get used to. Nitrogen, we didn't use in the last problem, but it's listed as 14.01 grams, I believe. Just double check that real quick. Yes. Hydrogen is listed as 1 mole is 1.008 grams. And oxygen is still 16, one that we're going to use quite often. Okay, so there's all of our conversions all set up. I show them in these little boxes to organize my conversions, to do dimensional analysis, as it's called. It's a pretty important procedure and a lot of simple math in some of the things we do in chemistry. But it's a way of getting from one unit to another and kind of organizing your numbers. And I don't show it here because it gets a little cluttery if I do, but of course the reason this works is because grams cancel out, and that leaves us with moles. And grams of nitrogen cancel out, and that leaves us with moles, and so forth. So you don't have to show those cancelings, but they're certainly there to confirm that you've set it up correctly. So they're really a nice way of knowing if you're not quite sure. If you're doing a new kind of problem with a conversion like this, then maybe it's a way of making sure you've organized your data properly and things will cancel out, so that you don't get a false sense of correctness when in fact you had something flipped over or something like that. So let's do the conversions. 0.694 divided by 12.01, typing a little too fast, gives us 0.0578. We'll go ahead and round that off. So 0.0578 moles of carbon. Now we should, speaking of rounding things off, we should mention that along the way as we go this year, it's going to be important at some point that you get a pretty good grip on significant figures and how we round based on the numbers that we have given at the beginning of the problem. So in this example, I'm rounding my answer to 0.0578 because the original mass I was given was 0.694, and we would say that has 3 significant figures. The 6, 9, and 4 are all measured values that we're certain of, and so in my moles conversion, I should have 3 digits that I'm certain of. In this case, the 5, 7, and the 8. The zeros are just there to bump things over. So if you're not familiar with significant figures, for now, just follow along with me and do your best. When in doubt, maybe keep an extra digit instead of rounding off so short, but make darn sure that you get significant figures and your rounding rules pinned down comfortably and confidently very, very soon. Otherwise, you're going to make mistakes with sig figs. And there are a few places in the AP exam where significant figures can come into play, and there's always at least one point in the free response section where rounding and significant figures will matter. Okay, so the nitrogen conversion, I have 0.090 divided by 14. That comes out to be 0.0064. 0.0064 moles. And again, I'm going to round that off because 0.090 has just 2 digits. This has just 2 digits. Okay, take those off for clutter's sake. For the hydrogen, we have 0.084. Sorry about that, typing a little quickly. And I divide that out. Hydrogen comes out pretty much always about the same because we're basically dividing by 1, but it's about 0.083 moles. And finally, oxygen, 0.308 divided by 16 gives me 0.019. I'll go round it off to 0.0193 moles of oxygen. So remember on the last problem that we did, we wanted to look here at this point for the smallest value of the 4. And obviously, if I look these over, nitrogen is the smallest. It's 0.00. The other ones all have just the 1 0. So nitrogen is the smallest one. Don't get too hasty about picking the wrong one. Otherwise, your ratios will look funny later. But we're going to go ahead and put that 0.0064 moles of nitrogen under all of the others. So that goes here, divided under the carbon. That goes here, 0.0064 moles of nitrogen. And again on the oxygen, 0.0064 moles of nitrogen. All right. And again, we don't have to divide it by itself. Some people show that. I don't see that it serves a real important purpose for us. Everything's going to cancel out. Mathematically, it becomes 1, and that's really silly. But the other ones we need to do. So 0.0578 divided by 0.0064 gives me a rounded off ratio about 9 to 1. So this is a 9 carbons for every 1 nitrogen ratio. And remember, we're looking for our calculator to give us here a whole number, maybe a half number, occasionally one with fourths and even thirds. You'll see that actually in the next problem. 0.083 for my second ratio divided by 0.0064, and that's a 12.97. So it's around a 13 to 1 ratio. So fear not, that's a little bit larger, but it's properly calculated, and it's very realistic that hydrogen could be present in compounds in a very large number. Hydrogens are teeny tiny, and they get tacked on everything in our compounds, and so to have a lot of them is not terribly unusual. The last one, you might be able to see, it looks like a 3 to 1 ratio to me, but let's just make sure we get that one right and double check it. It is a 3 to 1 ratio according to our calculations. So that's 3 oxygens for every 1 nitrogen. So I've got all my ratios that are needed now to write my empirical formula. It looks like I've got a 9 to 1 ratio, I've got a 13 to 1 ratio, and I've got a 3 to 1 ratio. Okay, so to write my formula, I'm going to stick with the original order. Again, up here in the problem, it was carbon, hydrogen, oxygen, nitrogen. So I'm going to go ahead and say carbon, hydrogen, oxygen, nitrogen for my empirical formula and give them the proper numbers from the ratio. So according to this, 9 carbons for every 1 nitrogen, 13 hydrogens for every 1 nitrogen, and 3 oxygens for every 1 nitrogen. Okay, there's our formula. That's our empirical formula. And again, like in the last one, we were being asked to do one more calculation, but as far as question A is concerned on our instructions here, we've done what we're being asked to do. That's the empirical formula, a 9 to 13 to 3 to 1 ratio for our compound in this problem. All right, so to do the next one, we need a little bit more space here. So let's see if we can clear out a little bit of room. Move question 3 down just a touch. Give us enough room to finish this one up. Okay, so I'm going to switch over to a different color just to finish this problem up for B. And so remember, the molecular formula is a sum multiplied version of this. We need to figure out how does the molar mass of this compound compare to the empirical formula's mass of this compound. So again, you wouldn't need to write this out. I'm going to do it just this one more time and say that the molar mass, which we're given is 183.2, divided by the empirical formula's mass, slightly abbreviated here there, which we'll need to add up, and that'll give us some multiplier. So the molar mass in the problem is given as 183.2 grams per mole, And to find the molar mass, or rather the empirical formula's mass, I'm going to need to go to my calculator and add up all of this. C9, H13, O3, N1. So jump back over here to the old TI and say I need 9 12.01s, that's my carbons. I need 13 1.008s, that's my hydrogen. Plus I need 3 oxygens, those are 16 exactly. Plus I need a nitrogen, which is just a little over 14. Oops, 14.01. Survey says 183.2. So what do you know? We've got a compound here whose molar mass and empirical formula's mass are the same thing. And that means that the multiplier is 1. That means the empirical formula and the molecular formula are the same thing. Essentially, we're going to take, as we did in the last problem, this formula times 1, and that gives us the same formula again. C9H13O3N1. And I mentioned in the last video, you don't need the 1 on the N, but you're certainly welcome, and I'm going to say encouraged, to write the 1 on the N so that you don't make a mistake when you do have a multiplier that isn't just a 1 here. So that's my molecular formula. And I have both answers that I need, I believe, to the problem. This is a good habit to get into. Double check that you've actually answered what the question's asking you for, because occasionally you'll think you know what it's going to ask for. You can, I've done so many of these, I just know what it wants. And you actually give it something you didn't want, or you don't give it exactly what it wanted, or enough of an answer, and you might come up short. And on the free response questions that we're looking at, like these big problems on the AP exam, it's going to cost you 1, 2, 3 points, who knows how many, just because you didn't double check. So I want to double check that this is in fact what I was asked to do. Calculate the empirical formula, got it. And what is the molecular formula? We got it. So we've got both of those done, and that's question 2. All right, we'll come back on video on the next video with problem number 3, and you'll see it's quite like the ones that we've just done with a little bit of a twist on the ratios. See you then.